students. I am Dr. Shikha Pandey, Associate Professor from Institute of Aeronautical Engineering. So, in this lecture series of this subject, solid waste management, today I will discuss about the landfill gas modeling. So, previously I have discussed about the collection of this methane from the landfill. Because from the landfill, what happened at the initial phase, aerobic condition will be there. For when the oxygen deficiency will occur at the landfill, then this aerobic condition starts inside the landfill. So with this anaerobic condition, methanogenesis process will start, and with this methanogenesis process, methane production has been started into the landfill. So this methane is like a very dangerous gas because it is a greenhouse gas, and this methane production will create nuisance and odors in the vicinity of the landfill area, and that will be in this way it will create very anesthetic condition for the local public and the local people. That's why this monitoring of this methane gas is very mandatory, and the monitoring of this methane gas is mandatory as well as its monitoring is required, because this methane gas is a very useful gas. So if we can utilize this methane gas to some electricity generation, so to some other products, so that will be other beneficial effect of this methane production. So this methane gas, because this from the landfill too much methane has been produced, and for collecting this methane some wells has been made on the landfill site. So through the wells we will collect the methane, and some methane measurements method will be there. So in this today we'll discuss about the methane measurement method and the gas modeling methods. What are the modeling theories has been adopted for this methane measurement and this methane gas production? So first is the landfill methane measurement is a direct measurement of methane emission from the landfill. So directly measurement of methane from the landfill is this methane measurement. So for this, three types are there. First is the flux chamber testing, flume measurement and dispersion modeling. Flux chamber testing will be there, then plume measurement will be there, and then dispersion modeling will be there. So this landfill methane measurement is like a direct measurement of methane emission from the landfills, and this flux chamber testing is like the mass emission per area. At some point is there, at a point, from that point the landfill surface using the flux chambers will be there. Up this point is like the flux chamber will be there. Flux chamber is there, and this point, this methane flux or like methane mass emission has been collected or has been measured at a sample points. So the flux sampling methods are generally standardized. These flux chamber methods are basically standardized, but there are no industry accepted standardized methods for the extrapolation of site-wide emission. So this flux sampling method is like it will be generally standardized, but it has been not some industry accepted model will be there, or some standardized model will be there, method will be there for the extrapolation of site-wide emission. So this flux chamber is like some testing measure of methane. Flux means the emission of methane from a point source. A point source will be there. You can consider this point source is like well has been installed on the surface of the landfills. So from this well, the flux chamber will be there. The flux chamber testing measures will measures the methane flux or methane emission. It will measure the methane flux or methane emission. So this methane flux is a point at a point on the landfill surface, and these points will include the flux chambers. So the sampling methods are generally some standardized methods are there, but these methods are not much industry accepted or standardized method. But these methods can be useful for the sampling of methane from the wells from these landfill sites. So you can see this is a picture of the flux chamber. You can see this one vacuum pump will be there. So through vacuum pump, flow meter is there, and then mass flow controller. This is the mass flow controller. This will control the mass flow emission of methane, because this flux will basically means the emission of methane. So here it will be controlled, then it will enters into the many chambers, and from that chambers it is go to the surface flux chamber. You can see that this is a sweep line and their thermocouples are there. Here this methane has been collected, and in this chamber methane has been collected and testing has been done. So this is about the flux chamber testing. Sample line will be there. Through this line methanes are there, and these methanes has been collected and used for some other purpose. So modified flux chamber will be there, and this is the sample trains. You can see that this is a sample train. So through sample train this will enters into the chamber. Now next method for this methane measurement is the plume measurement model. So plume measurement methods are ground based optical sensors. These methods are ground based optical sensor, and it will be goes to measure the methane plumes. It will measures the methane plume. Okay. So this methane plume, this is basically coming from the landfill, and those plume measurement are then used to calculate the landfill's methane emission rate. So these plumes will calculate the emission rate. So the landfill where methane plume is coming from the landfill, and those plume measurements are then used to calculate the landfill's methane emission rate. So from these plumes the landfill methane emission rate has been calculated. And this plume measurement is a very simple method. So it will be like some on the ground where some optical sensors are there. So these sensors will able to measure the methane plumes. They will be able to measure the methane plumes, that plume coming from the landfill, and those plume measurements are then used to calculate the landfill's methane emission rate. Next is the air dispersion modeling. Air dispersion modeling can be used to determine the emission rates from the landfill. It will be determining the emission rate from the landfill. So this emission rate and these methods will monitor the on-site or some downwind methane concentration using a dispersion model. So from this will be like this monitors the on-site or downwind methane concentration using a dispersion models, and this will be going to calculate the methane emission from the landfill. So this will be going to calculate the methane emission from the landfill. This methods monitor the on-site and sometimes the downwind methane concentration using a dispersion model, and that model is to calculate the methane emission from the landfill. So this air dispersion modeling, this is all about the plume measurement and air dispersion modeling. Plume measurement is the method that is like the ground based optical sensors are there. These sensors are going to measure the methane plume that is coming from landfill, and those plume measurements are then used to calculate the landfill's methane emission rate. Like that, air dispersion modeling will be there. This air dispersion modeling can be used to determine the emission rates from the landfill. It will be used to determine the emission rate from the landfill, and this method are the on-site or sometimes downwind methane concentration. This will be using a dispersion model to calculate the methane emission from the landfill. So first is the landfill gas modeling zero order decay model. So in this model, how we will proceed? We'll proceed like this. We will assume that the waste is constant at the time t. So effect of waste as is not incorporated in the model. So in this model, waste age is constant, and this will be like this waste as age cannot be incorporated in that model. So age is not considered. Landfill age is not considered for this measurement. Okay, so it will be studied by this. This is the relation for this modeling method. where this Q is equal to methane generation. So methane generation meter cube per year per. So M is the total mass of the solid waste, and L naught will like ultimate methane generation potential. So potential of total methane generation. L naught is equal to potential of methane. Potential of methane. And this L naught is like ultimate potential of methane generation. Small t is equal to time. Small t is equal to time, and Ti is the lag time. Like the lag time will represent the time between waste placement and gas generation. Lag time is like year. It is in year. So the time between the waste placements and gas generation. Same thing is there. TF will be there. So TF is the time to end of the gas generation. TF will represent time for end of gas generation. This is the TF. Like Ti is the lag time, and TF is the time for end of the gas generation. So Ti lag time, that is the time between the waste placement and gas generation. Time between the waste placement, and then it's a generation of gas in per year. It will be represent the year only. And like TF is the time of the end of the gas generation. It should be also in the year. Like we have discussed about the post closure age, like 25 to 30 years of age, pre closure 15 to 20 years of age. So TF is like that. Next is the first order decay model. So in this model, the landfill gas generation in a certain amount of waste is assumed to decreases the exponentially. So this has been assumed to decreases exponentially. The first order decay equation is used as US EPA land gem. Q is equal to M L naught E K T minus T1. So where K is the first order decay rate constant. We already discussed about this. K is the first order decay rate constant. Modified first order model is the model that assumes that methane generation from a certain amount of waste may be initially low due to the lag phase. Obviously, in this model, it has been assumed that the generation of methane from a certain amount of waste for up to a certain generation of the waste, up to a certain time, the waste generation maybe initially it will be low due to the lag phase. Because initially what happened, it is totally aerobic condition will be there. Initially, in the initial landfill, aerobic condition will be there where oxygen is available. So in this way, the waste, the methane is not that much. Methane production will be less. So it has been pointed out that the methane generation is maybe less because the sum of the amount of waste may be initially low due to the lag phase. Like that, you can come here with the generation of this gases is like rise of peak before declining exponential, like in the first order decay model. So the generation of methane generation, then methane generation will be like, it will be rises to up to a peak. So before declining the exponential, like in the first order decay model. So before declining the exponential in the first decay model, K M naught K plus S is there, where S, again same method will be there, 1 E minus S, T minus Ti, Ke, exponentially like K T minus Ti. This is the whole paragraph, whole equation for this first order reaction. So first order K will represent the first order decay constant, and S is the first order rise phase rate constant. First order multi-phase decay model will be there. The first order multi-phase model will assume that different fraction of the waste decay at the different rates. So different fraction of the waste will decay at the different rates. So the waste is divided into 3 or more fraction. So depend upon the rate of its decay. So decaying first order multi-phase decay model. So in this decay model, the first order reaction is like a multi-phase decay model, and it is assumed that the different fraction of the waste will decay at the different rates, and this waste is divided into 3 or more fraction. So it will be divided with 3 or more fraction, and depending on the rates of their decay. So depending on the rates of its decay, the first and multi-phase decay model will assume that different fraction of the waste will decay at different rate. So this is the equation for this first order multi-phase decay. You can see this is the first decay and this is the second decay. So waste is divided in 3 fraction depending upon its rate of decay. First fraction is initial, then after some, then after some. In this way, this waste will go to will divide into different fractions. So next is the LandGA model. LandGA model is like, it is a simple first order decay equation. So in this, what is the input? Input parameters are the potential methane generation capacity, that is L naught. L naught is the potential methane generation capacity, and it describes the total amount of methane gas that will be potentially produced by the metric tons of waste as it decays. So this methane gas will be potentially produced by metric tons of waste, and when it goes to decay. The methane generation rate constant describes a rate at which the refuse decay and produces methane and is related to the half-life of the waste based on the equation like half-life. Half-life is equal to divided by total K, and K is the rate constant. So K rate constant of this methane generation. So 2 are the input parameters for this LandGA model. First is the potential methane generation capacity. Potential methane generation capacity, it basically describes the total amount of methane gas that will be potentially produced by the metric tons. So this will be potentially produced by the metric tons of waste, and then it starts decaying. And the methane generation rate constant K, it will basically describes the rate at which the refuse decays and produces methane and is related to the half-life of the waste, and it is based on the equation. You can see this is the equation. This is the table for the default type, like which type of landfill will be there and how much amount of lag phase L naught methane production will be there. So this table will represent the landfill types and the production of methane. So it is, and the value of K in a year. So conventional is like if a rainfall is more than 25 every year, in a year, more rainfall will be more than 25 centimeter every year, then the ultimate methane production is 170, and its K value will be 0.5, not 0.5. Arid areas, in arid areas, if the rainfall will be less than 25 inch per year. So this is the arid area. So in this type of landfill, again the methane potential will be like 170. Next is the conventional rainfall, like more than 25 inch per year. So it is inventory type, and here the methane production will be 100. Ultimate methane production will be 100 meter cube per mg. Again for arid area and wet area. So in the wet, like in the bioreactor, so this is inventory. This all are like inventory methods. So conventional, arid area, and wet reactors. So these type of default types are there in this landfills has been made, and what are the ultimate methane potential from that particular landfill has been collected, and that landfills has been discussed here. You can see that. So you can see that the default type is with the default types are like CAA and inventory, and in both of the case, conventional arid area will be there, and from that what is the ultimate methane potential, L naught will be there, and the K value will be there. All these are like per year. So, and now comes to the next point, which is about the assumption. For this LandGA model, we assume that the waste is completely homogeneous, so that the L node is assumed to be constant with the time and space, with space and time. And this model does not include the categorization of waste. Categorization is not included. So this is the assumption, this is the limitation in this land GEM model. And this land GEM will assume that the waste composition will affect L node and not K. So this land GEM will affect the waste composition and L node, not the constant, okay, K. And next point is that the default value that separately for the variation in moisture content, that will separates the variation in moisture content due to the rainfall or leachate circulation, but do not account for the variation in temperature and waste composition. So next point is that the default valves, that is separately for the variation in moisture content and due to the rainfall or leachate recirculation, but do not account for the variation in temperature and waste composition. Land GEM may not be appropriate for countries with significant different climate or different mix of waste type. So it will be not suitable for our country, because in our country waste is of different type of waste are there, and the climate is also very much variation in the climate. So in this, the assumption is that the waste total waste amount is completely homogeneous, not heterogeneous mixture. Homogeneous mixture means the mixture which is of the same fixed deposition, which is of the same proportion. But in heterogeneous mixture, most of these are not indefinite mixtures are there. So for this methods, for this modeling, the waste should be homogeneous and it should be assumed that it will be constant with space and time. So if we will go for this type of modeling for in our for the climate of Indian climate, then in that what happen, this won't be constant. This L node won't be constant with time and with space, and this will be like rainfall and the value separately for the variation in moisture content due to rainfall or leachate recirculation. So due to rainfall or leachate circulation, but it will not account for the variation in temperature and waste composition. It will not contributes toward the variation in the temperature and the waste composition, and this will be not appropriate. Obviously, because of that reason, this modeling method is not appropriate for the countries which will be having significant climate or different mixed type of waste will be there. Next model is the IPCC model. So this model was developed for countries to estimate the methane emission from the waste disposal using regional per capita waste generation rates and population estimates with deduction for the landfill gas collections and oxidation. The model was developed for the country to estimate methane emission from waste disposal using regional per capita waste generation rates and population estimate with deduction for the landfill gas collection and oxidation. It uses multi-phase first order decay model. It basically uses the multi-phase first order decay model. It incorporates the degradability of waste components and waste composition while computing the methane generation rate. So it will be like gives the information about the degradability of waste components and waste compositions. So waste component and waste composition, it will gives the information, and the while computing the methane generation rate, while we are calculating the methane generation rate. So input parameters, what are the input parameters is like K value for rapidly degrading waste, slowly degrading waste and moderately degrading waste. K value will be there. Slowest, moderate or rapidly. Degrading waste. So this IPCC model has been developed for countries to estimate the methane emission from the waste disposal using some regional per capita waste generation rates and population estimate, and it will be like reduction in the landfill gas collection and oxidation, and it uses the multi-phase first order decay model, And basically it incorporates the degradability of waste components and waste composition. And this will be, while computing the methane generation rates, the input parameter is like the K value will be there. This K value is for rapidly degrading some of the waste, slowly degrading some waste, and moderate and some rapidly degrading waste. Okay. First approach is that it will be assumed that the degradation of different type of waste is dependent or is influenced by each other. So first approach assumes that the degradation of different type of waste is like it will be dependent or is influenced by each other. Second approach will assume that the degradation of different type of waste is completely independent of each other. So first is that we assume that the degradation of different type of waste is dependent. Degradation of waste is dependent. And second approach is degradation of different type of waste is completely independent. So both are the same type of waste is dependent. Same type of waste is dependent. Is dependent on each other. And next is the different type of waste is independent of each other. Different type of waste is equal to independent on each other. So, and as it will be degradation of different type of waste is completely two conditions are there, dependent and independent. So same type of waste will be there, they are dependent on each other. Different type of waste are there, they are independent to each other. So what are the limitations for this IPCC model? So this IPCC model, 4 climate categories represents an improvement over land gem. 2 climate categories approach limitation exist, and it will include 2 types. First is the temperature has a smaller input on landfill gas generation than precipitation, and it should not be assigned equal weight in assigning climate categories. And temperature is having a smaller impact on landfill gas generation. So then the precipitation, and it should not be assigned equal weight in assigning climate categories. Second is the PET data are usually not available for most location and should not be a basis for assigning climates in temperature region, even if they are scientifically more valid. So these are 2 points which is the limitation of this IPCC model. Temperature having smaller impact on landfill gas generation, then it will precipitation will be there, and that should not be assigned equal weight in assigning the climate categories. PET data are usually not available for most location and should not be basis for assigning the climates in temperate region, and even if they are scientifically more valid. So if we consider that 1000 mm per year precipitation will be there, and the threshold for separating the tropical climate into dry versus wet category is better than the land GM threshold 635 mm per year, but is likely too coarse to account for the effects of precipitation across the wide range of values that will be encountered. So most of the models automatically calculate collection efficiency based on the answer to the following factors. Mostly model, it will be automatically calculate the collection efficiency based on answer to the following factors. So first is the overall site condition, like dump site or managed landfill site. Waste depth will be there, waste compaction practices, size of the tipping area, and bottom liner type. Overall site condition is there. So dump site or managed landfill, and what is the waste compaction practices, size of the tripping area, and bottom liner type. So these are the some factors on which most of the models has been automatically depends. Next point is the percent of disposal area with operating extraction wells, percent of disposal area with daily, intermediate, and final cover, and evidence of the elevated leachate levels. So these are the points on which it will be totally depends this type of models, and on this these are the points on which we are considering all the models. So this is all about this lecture. These are the some of the list of the references, some of the references of the textbook that you can follow for this study, because this textbook will give you some in-depth study of these topics, and you can go get some more knowledge about these topics. So at this point I am concluding my lecture. In this lecture I have discussed about the different modeling methods that has been used for this study, and what are the different modeling methods, and that modeling method will depends upon the characteristic and the climate condition of any area. Okay, so if you have any query, if you have any question, you can write in the comment box, or you can directly mail me onto my given mail id shikha.pandey@gmail.com. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.